Slot fill factor. On the surface, this sounds like a manufacturing detail. How much copper you actually manage to cram into a slot, compared to the slot's total cross-sectional area. But this one ratio turns out to be one of the tightest, most fundamental constraints in the entire motor design process. Formally, the bare wire slot fill factor, kWb, is defined as the number of turns times the bare copper cross-sectional area divided by the total slot area. It sounds simple. What it actually limits and what it reveals about copper losses is genuinely surprising, and that's what today's episode is about. Here's an obvious question. Why can't you just fill a slot completely with copper? Look at the diagram. Round wire, packed as tightly as geometry allows in a square grid, tops out at a covered wire fill factor of pi/4, about 79%. That's not a manufacturing limitation, that's pure geometry. The unavoidable gaps between circles packed in a grid. And that's before insulation, slot liners, or corner effects even enter the picture. There are actually two definitions worth knowing. Bare wire fill factor uses just the copper cross-section, because that's what actually carries current. Covered wire fill factor includes the insulation too, because that's what determines whether the wire physically fits in the slot at all. Here's the genuinely surprising result hiding inside this topic. Work through the algebra, and the power dissipated as heat in a slot, the I²R loss, turns out to be completely independent of the number of turns, N. Look at the equation. There's no N anywhere in it. Just resistivity, fill factor, current density squared, and the volume of copper. How does that happen? Slot resistance scales with N², but for a fixed total ampere turns, the current in each individual turn scales with 1/N². That's 1/N². The two N² terms cancel exactly. And here's a connection worth remembering. This is the exact same underlying fact that made the torque constant misleading back in episode 4, and the reason the motor constant stayed independent of turns in episode 5. All three trace back to this one relationship. Since more turns doesn't directly buy you better efficiency, what about wire gauge? Here's a real trade-off worth understanding precisely. At a fixed slot fill factor, moving one wire gauge thinner from gauge G to gauge G+1 lets roughly 26% more turns fit into the same slot. Sounds like a win. But that same one gauge step increases the winding's resistance by about 59%, a dramatically steeper cost than the modest gain in turns. The lesson here is that wire gauge and turns count aren't a free lever in either direction. Going thinner buys you more turns, but it costs you resistance at a much faster rate. Let's close with what actually matters in practice. First, aim for realistic targets, not the theoretical ceiling. Without incurring extreme cost, a bare wire fill factor around 50% and a covered wire fill factor around 60% are achievable in practice, well short of that 79% geometric limit. And that gap is exactly what slot liners and real-world winding technology cost you. Second, remember that turns count N doesn't change copper loss directly, but it still changes everything else that matters. The back EMF constant, the torque constant, and how well the motor matches your supply voltage. Slot fill factor is the hard physical ceiling. Every one of those winding decisions ultimately has to fit inside. And finally, remember the connections. This same N independence of copper loss is exactly what made the torque constant misleading in episode 4, and what kept the motor constant independent of turns in episode 5.